Now let's move to the case of higher dimensions and double integrations. Again, I expect you to know about double integrations from before, but I will give a quick review regarding how double integrals are calculated and what they represent. If you are using Cartesian coordinates, then double integrals are written as follows. Integral and another integral of some function of x and y. This time, here we have dx, dy. Here we change x from x1 to x2. And here we change y from y1 up to y2. Now, what this double integral is really trying to do is trying to calculate the volume under some curve or under some function. So here you are in 3D. You have the x-axis, you have the y-axis, and you also have the z-axis or the height. And here you can have, let's say, x1, here you can have x2, then you can have here y1, and here y2. Then you have some area enclosed between those limits. So you have this and this, then you have this and this. And now this is your area. This yellow thing is your area, and above this area you might have some function in 3D. So you might have something like that. Now double integration tries to get the volume under this area. So let's say this maps to this maps to this maps to this, and this maps to this. Then you have this intersection right here, and you want to get the volume under this part of the function. So this right here is the function f of x and y. Now let's review how this double integration is evaluated and then give a more intuitive understanding of our way of evaluating double integrals. So suppose you have an integral right here, integrate from, let's say, x equal to 0 up to x equal to 1. Here you have from y is equal to 1 to y equal to 2 of the function, let's say, x multiplied by y dx dy. So what we do first is try to evaluate this inner integral right here, and we are integrating with respect to x, and so we assume that y is constant. So to do this integration, you will find out that this is equal to the integration from y equal to 1 up to y equal to 2. The integration of this with respect to x is equal to y x squared over 2, and we substitute from x equal to 0, from x equal to 0 up to x equal to 1, then I have dy right here. Now, it's easy to see that this integration or this value right here will be only a function of y because we will substitute by the value of x. So let's do the substitution. We will have this being equal to the integration from y equal to 1 up to y equal to 2. Here I can have y over 2 multiplied by 1 squared minus 0 squared, so this is equal to 1 minus 0 or 1 squared minus 0 squared dy. So this is equal to the integration from y equal to 1 up to y equal to 2 y over 2 dy. Then we can perform this integration to be equal to 1 over 2 y squared over 2 again, and we evaluate this from 1 to 2. So now this is equal to 1 over 4 multiplied by 2 squared, which is 4 minus 1 squared. So this is equal to 3 over 4. So the volume under this function, under this xy, given those limits for x and y, is equal to 3 over 4. Now let's see what is really happening during our evaluation of the double integral right here, and I'll use this same picture again. So let's get this and talk in general. So here I have the y-axis again. Then I am evaluating the general integral here of f of x and y dx dy. Here from x1 to x2, then from y1 to y2. So first, we are evaluating this inner integral, right? So this is an ordinary 1D integral, and we are moving in the x direction. So what we are really doing is that we are partitioning every plane or every slice like that into small rectangles and getting the areas of those slices for different values of y. So for example, I am getting the area of this slice right here, this front slice. I am also getting the area of this backward slice. We are getting different areas at different values of y. That's why this integration right here turns out to be a function of y only, because at every different y, the height of the function is different in general, and so the area of this front face will not be equal to the area of this backward face. Very well. Now, after this first integration, you are integrating in the direction of y. So what you are really doing is that you are using the areas obtained in the first step, and you are multiplying every area of those by a very small distance like this called dy. This dy, this delta y. So multiplying this area, for example, by this dy will give you some very small volume, right? And if you choose this dy to be very small, then this volume can be approximated as a volume of some cube or some rectangular parallel pipe. And so if you add all those volumes, so you are getting dy, another dy, and so on, and if you add all of those volumes, you get the complete volume under your function. So by the first integral, you get the areas at different values of y, and then by the second integral, you create small volumes and then add all of those small volumes together until you get the final volume. Now, you could have changed the order of calculations, right? So you could have the same picture again here. Here I have y again, and instead of partitioning this front face and the back face into small rectangles, I could have partitioned this right face here into small rectangles, and then I could have calculated the areas of those slices at different values of x. So I could have changed the integration to be the integration of the same function f of x and y, but I could perform the integration in the y direction first and then in the x direction. So here I can integrate from y1 to y2 first, then from x1 to x2. So by this, I evaluate this first, getting the areas of all the slices at different values for x. Then after that, this function will actually be a function of x only, because I will have substituted by some numerical values for y. After that, we will multiply the area of every slice of those by some change here, some dx in this direction, some very small dx, to get this small volume. So this will be a very small, let's say, cube or rectangular parallel pipe. And if we choose dx to be very small, then we could imagine that this is really some rectangular surface like this, without this irregular portion right here. So if I remove this, I think I can remove this. So I can remove this, I can remove this. I just want to color this irregular portion to make it clear what we are doing and what we are not doing. So I have this and this. Then I have this irregular portion. And if I choose dx to be very small, then we could get rid of this portion, this 3D portion right here, and imagine that it doesn't exist. And then after that, we add all those volumes together, because we have dx here, another dx here, another dx, and so on. So we add all of those volumes until we get the complete volume under the function. So that's it about the geometric meaning of double integration. In the next video, we'll start talking about variable substitution in double integration, which will lead again to the Jacobian matrix.